Hello and good afternoon, everyone. My name is Ashley Thompson, and I am a data scientist with the Applied AI and Machine Learning team here at J.P. Morgan. I am so delighted to have you all participate and here with us today to learn a little bit more about the next step on our data journey, to hear a little bit about our spotlight on data organization and storage. I'm sure if you've tuned into a couple of our events already, you are starting to get a theme around how important data is in your organization and what the critical considerations are along the way. And I think there's almost nothing as important as how we're thinking about storing and organizing our data. Without that, I think we're a little bit stuck in our tracks. So I'm really excited about this session and eager to learn more from our amazing subject matter experts that we have here today. Before I introduce our great subject matter experts, we'll hear a little bit from them and then we'll really focus a lot of our time today on a Q&A. So please, as you're listening or you have questions, please just type in your question. There's a little Q&A with little speech bubble boxes at the bottom of your Zoom screen. Feel free to ask any question that comes to mind. We will get through as many as we can in the time we have allotted. The sessions that I've been on already, we've had some great discussions and really interesting questions from the audience. So I know that this will be no exception. And with that, I would love to introduce today, we have Salim Fakhali from Bloomberg, and then we have Nick Dowler from J.P. Morgan, and they'll be taking us through some key tenets and what is important to understand around data organization and storage. So without further ado, I hand it over to Nick and Salim.
Nick, please unmute.
Thank you, Ashley. Can we have the first slide? Can we have the next slide, please? So there's a couple of sessions, a couple of goals for today. We're going to walk you through some best practices with respect to organization and storage, and particularly some database technologies. We'll give you some idea of what good practice looks like, some pointers towards what are the things to focus on, and also we'll introduce a few polls to see where everybody is, generate some questions and some insight from that as we go through the presentation. So can we were going to start off with a poll. So can we have the first poll up? So what we're really asking here is what kind of technology are you using for organization and storage today? Just to give us a flavor of where people are on their journey, whether they're starting out, whether they are a bit more advanced, and we can use this as we go through to create some examples and some talking points. So it seems that we've got quite a lot on the relational databases, which is good because we've got some very focused topics on that, and it's good to see some people are still using Office documents. We use a lot of Office documents, and some of the principles we're going to talk about today equally apply to that. And as Salim goes through some of the database technologies, we'll see some of the advantages of using some of the other types of storage as well. So I think that'll be quite helpful as we go through it. So we're going to start with data organization. And if we can go to the next slide, please. Sort of one of the key areas of data organization is how we describe it. And typically the way we describe data is through data modeling. We also call it data specifications. And the best practice in this area is to kind of have 3 levels of data models, and I'll go through each in a bit of detail to give you kind of an idea of what it is, how it's used, what it's for, how it can help. We call them, these are kind of, we'll talk about the words. So the first level we talk about is conceptual, and the reason it's called conceptual is because we're talking about concepts of things. So in the example we've got here, we've got the concept of customers and orders and people. We could equally, in banking, we have the concepts of statements and postings and transactions and payments and things like that. So at the conceptual level, all we're really doing is talking about the terms of the data concepts, what they mean, and also the relationships between them. And we can see here we've got some very, very high level relationships between these things to say how they relate to each other. So really, if you're in any business, there's always some concepts you are important to you. There's some concepts that could be important to you but owned by other people. And really the conceptual model is a way of expressing the things that are important, how they relate to each other, and we'll come on to aspects like ownership and things like that, how it relates to the conceptual model. So then the next level of really detail is what we call logical. And what we're doing at this finer level of granularity is taking each of the concepts, and now we're starting to show some of the characteristics of each of them. And so, for example, here we've got customers could have IDs, people have got names, there are relationships between them. These little wands mean that these things are mandatory, so people must have names, customers must have IDs. And then the things after the colons, they're what we call data types. And so they're saying that this particular field of data, this first name, it's got to be textual. It's mandatory and textual. So you can see as we get this next level of detail in data modeling and how we organize the data, it's starting to now express the actual points of data and how they're represented. And to a point, these things like what we call the mandatory optional aspects of it is starting to get towards what good looks like. You know, if you don't have names on people, we can't do a lot with it. If we haven't got IDs on customers, we can't do a lot with it. So we're starting now to edge into aspects of data quality. We're starting to edge into more finer level of granularity, but we're away from an implementation level of detail. So we're not saying that this data is in a database. We're not saying this data is in a spreadsheet. This data is in a file somewhere on a file system. We're still keeping the description of the data at a very logical level, just to give us a data definition. And on this, we're probably going to put things like definitions. We're going to explain what these things mean, and we're going to provide all those descriptions. So if anybody comes along and says, tell me what this means, tell me what good looks like, I can point you to this specification and say that's what it looks like. This is the data that we need in order to operate this business. And so this logical layer is something we always try and produce. We always try and keep it available for people as reference, as well as helping developers develop solutions for us on technology platforms. Then the next level of detail is physical. And here, what we've got is the data how it's actually represented in a database, in a file, in a spreadsheet. And you can see now that we're starting to get into technical jargon, right? We're starting to use the terms used by the technologies. The varchar now is a data type that represents textual information in a database. Instead of saying integers and numbers, we've got int. So we're getting to a point where this is really a technologist domain. And really, technologists have to interpret the logical and then convert it into the implementation. And often we can have these levels without the other one. Sometimes people give us a database and they don't give us any logical, right? All we see is a table called cust and a table called person. We don't know what these things mean. We don't know what's mandatory. So as you can see from the levels, each level provides a level of description. And typically the higher the level in the middle, the logical level, gives us the highest level of detail. The physical has removed some stuff. We don't know what's mandatory potentially anymore. we've lost the definitions unless we've somehow copied them through. And so really all the levels work in harmony to give us a complete description of the data and how it relates to each other. So if we could have the next poll, and if you, next poll, please. If we could, now I've kind of given you a level, a description of the data modeling levels. Perhaps you could just say what sort of level you think you're at the moment. Have you gone all the way to the physical? Are you still stuck at the logical? Do you think or have a conceptual? Or have you doing no data modeling at all? And this is a brand new thing, and we just use the data in the files and use the data in the databases, and we don't have definitions. So it's good to see that there's some conceptual modeling going on. Sometimes that can be missed. People don't often tend to see the value of it until you get to quite a large organization. I mean, I expected an amount of none. I equally expected, an amount of logical and physical. So maybe we can have some conversations about that sort of leveling of data modeling as we go through. So can we go to the next slide, please? So why model? I've got a few, this isn't exhaustive. These are just a few things that I think have been the most important reasons to model. There are others. Let's just go through a few of these. A description of data. Whether we store some data in a database or in a file or wherever we put it in whatever technology, that data it's always got the same characteristics, right? If I'm storing a payment in a database, I'm going to have the account numbers on it. I'm going to have the amount. I'm going to have the currencies, and so the form may change, where we store it may change, but hopefully the definition of the data remains consistent, and that consistency is really important. And so the logical level and certainly the conceptual level gives us that independence of implementation for data description. So another thing that's very topical is classification of data. So typical classifications of data can be things like sensitivity, and that can be sensitivity in terms of personal information or sensitivity in terms of confidentiality. If we know which of the fields are going to carry this kind of classification, then we can take action. So, for example, we may encrypt it, we may obscure this information, and so knowing in the specification of the model which of this data is under these conditions, then we can treat it accordingly when we move it or we store it. And so that's a key in terms of knowing how to treat the data. So another aspect is what we call data type definitions and constraints. So in the example I showed you earlier, I got some names and I got some identifiers. So what is a good surname? Can you have a piece of text that's 500 characters long? Can it be one character? Could it include special characters like ampersands and asterisks and all kinds of stuff? Does it look like an email address? So if we can define what good looks like in terms of these characteristics of these data fields, then we can apply what good looks like against the data and say, yep, this is good, this isn't so good. And then we can start to increase the data quality of it and get agreement of what good looks like in the model before implementation. So another thing, we touched on this I touched on this briefly with the conceptual model, is means of defining ownership. And so at the conceptual level, if I know that this particular data is owned by this team and this particular data is owned by this team, or this particular data is owned by a third party, then I know who can deal with issues on it. I know who to go to. I know who to ask about if I don't understand the definition or there's an error in it. And then I can start to join and collaborate and get people to understand what it's being used for. Maybe there's entitlements on it. I need to ask for permission. Maybe there's some kind of licensing agreement. And so I need to go to the owners and know who those owners are, and I can do that typically against the conceptual model or the logical model to find out that ownership. A very big use case is in terms of change management. What happens if analysis is always being asked? What happens if I remove this field? What happens if it becomes optional? What happens if I need to remove it from your view for some reason? Do you need it? Are you using it? These scenarios of change management, if we can use the models to help us understand what the impact is, then we can plan. We can understand that, yes, this could be removed, this could be optional. We get greater freedom. We could potentially have greater control. We can start to filter who gets what. We know who's got what. We can then plan the change accordingly. We've done a bit about data quality, and I know there's been some other sessions on data quality as part of this series. And we saw in the logical model, we started to introduce some aspects of data quality with optional, mandatory, but we can go further. We can say, this is only valid when we've got both of these fields. This is only valid, this file is only valid when it's got so many people in it. This file is only valid when it's got so many payments in it. The total value has to be this. And we can start to describe what those rules are against the model for data quality. The next one goes along with ownership. We call it data authority and system of record. We use the conceptual model to say what systems are the systems of record to go to. And so if we were getting, if we need client data, we have a client data golden record. We call it a system of record, and we know where to go to, and we've got a directory of that, and we can say, what is the golden record for this data? And it would tell us where to go to get it. So this helps people, particularly in data sourcing, find the right place to go in the organization of data across the enterprise. And so another reason that we need the conceptual model, we need the logical model in order to express this kind of ownership and location of getting data. And then finally, but certainly not the only one I could probably go on, is, and this is quite pertinent for a little example we've got at the end, is the definition of identifiers. How do we join data? And what do I join data on? And how do I know how to join data from one place to another? And what good looks like for these identifiers. And we'll go through an example of that in a minute. So I think, can we have the next poll, please? So this question is about, if you do model and you keep these data definitions, how do you model? Do you use tools like data modeling tools? Do you use spreadsheets? There's a lot of Excel data modeling tools out there, right? They specify the fields of the data, the definitions, the lengths of the records, whether it's optional, mandatory. Or do you use no modeling tools at all? What's the level of modeling tools that people use today? So interestingly, the result of this is quite typical, actually. There is a lot of modeling done in Office documents, specifications. Could be Office documents for saying this is the specification of the record. Modeling tools are certainly prevalent. We try and encourage them. We try and at least have modeling tools that are dedicated to specific purposes. So if you need to do a conceptual model, we have a conceptual modeling tool. If you need to do a logical model, we have a logical modeling tool to keep the experience tight. The technical tools, that's things like XML schema editors, things that are very technical, usually physical modeling. And so it's interesting, we got a lot of Office documents for modeling. That's we've got quite a bit of that too. So that's interesting. So go to the next slide, please. So key considerations. So model within the domains. We'll see an example of what this means in a minute. So keep the data sets independent, model each one independently. When you're storing data, co-locate it, don't co-mingle it. So don't create some hybrid. In the example I had before of people and customers and people, don't combine those attributes together into a person customer kind of thing. Keep them separate, keep the relationship. And the reason for that is because, one, you can keep the data as it was given to you, so you know what was provided to you and you haven't done anything to it. And then you can manage the relationships. Keep the logical independent technology. This can be hard, but really that logical is the implementation independent specification of the data. It will change for each place we locate it, each place we move it with technology. And so there's always typically many physical models for a single logical, to try and keep that separation of concerns. Which really goes to the next point, keep implementations for the special considerations. When we do, one thing I didn't put on that first diagram of the data modeling levels is the links between the levels. So we really do need to know that this table in a database really does mean that logical thing, which really does mean that data concept. Being able to do that then helps us with the change management aspects, helps us with data discovery and inventory, knowing where data is across your organization. And also the last 2 points I think are particularly pertinent, because there can be a tendency to get perfection the first time round. And really these 2 points are just saying, be as good as you can at the time and be as accurate as required, because we can always go back. We can always add more to the model. We can extend it, we can add more, we can improve the accuracy of it. We can get better descriptions, we can increase the accuracy of the rules. And so really try and get a first cut that's representative but not perfect, and then move on and iterate. So I'd say that's an important point. Some people tend to sometimes get bogged down in data modeling because, you know, we need to express every possibility that could happen rather than the reality of what we've got in front of us. And it's really about just describing the reality of what we've got in front of us. So if we go to the next slide, please. This is just a trivial example of what I've kind of been talking about. So we've got a use case where I've got a donor's making a pledge. They may or may not send a payment. The payment goes to their bank. Their bank will do the transaction to do the credit and the debit. The credit will appear on an account, the fundraiser's account, and it will be, then that credit will show on a statement, and the statement you can get, so you know what payments have been received onto the account. You know what you've got in terms of pledges. So how do we join the data together? in this particular example, we're saying we've got a reconciliation where the donor name has to be the same as the posting payee. So that should give us a join to then know how we can bring these two things together. And so if we just go to the next slide, then the kind of best practice I've been saying on the previous slide, we've got these three domains. We've modeled them independently. We've said the relationships between them. We've described the attributes and what their data types are. So now we know we can use these donor names as identifiers, and then we can eventually bring it all together and then get the data consistency. Sometimes this works, sometimes this breaks, sometimes we do this kind of model and we realize we've got nothing to join on. We've got to create something or find out how we could do the join. But here we can see this consistency really does give us the power of joining the data together, and the descriptions of each domain helps us to do that, even way before implementing something. So if we can have up the next poll, please. So how does your data join together? Is it good? Is it logically joined, as I've said here? Does it actually physically join and we've got it joining? Is the data integrity all good? We've got no problems with it. It doesn't, because we don't have these common identifiers across things, or just don't know. So let's get some output from that. So interesting. We've got some, it does quite a lot of 50%, it doesn't, don't know. Small amount that it physically joins, but logically does not. And quite a bit of logically should join, but probably physically doesn't. So, I mean, this is typical. Hopefully the models can help us. The organization of the data can help us. If we've got descriptions of what the data is we need to join on, maybe we can improve this. Maybe we need to introduce additional data in order to do the joins. We can have that conversation through the models. And so can you go to the next slide for me, please? So this kind of wrapping up my section, I've really given you hopefully some reasons for data consistency, and really that goes back to the models and the specifications at all those levels. And hopefully those models together can help us answer a lot of these questions. Where is it? How do I use it? Who owns it? Where is it? What's the best place to go and get it? What does good look like? We can answer a lot of those questions using the models. And without it, it's difficult to join data, it may be impossible. And so if the sooner you can get on that kind of modeling journey, start to produce those, start to extend them, improve the quality of them, get them linked to the data, then we've got a structure for organization going forward. So with that, I'll hand you over to Salim.
Thank you very much, Nick. Can we go to the next slide, please? Thank you. So we're going to discuss in this section data storage, and we're going to start with relational databases. Basically, 85 to 90% of the world runs off of relational databases. So what are relational databases? They're a type of database that organizes data into tables made up of rows and columns, right? And these tables are linked together through relationships, defined relationships that Nick referred to as joins. Now, there are three important features of relational databases. The first one is the primary key, the second is the foreign key, and the third is the join. So what is a primary key, what is a foreign key, and what is a join? If you look at the schema in this slide, you'll notice that in the donor details table, there's a column ID, and this column is unique to every single row. And that is exactly what a primary key is. Think of a primary key if a row in the table is your postcode, then the primary key is your house number and street number. Right? It's unique, it's specific. It cannot be duplicated. Then we go to what is a foreign key. Now, a foreign key in one table generally refers to a primary key in the other table. So if we look at the credit card details table, for example, you'll see CCID, that's a primary key. But then in the donations table, those two primary keys become foreign keys, right? Now, how would you join these different tables using those defined relationships? Well, you would use a join. Some of you might be familiar with an inner join or an outer join. The most common is an inner join, which is basically if you think of each table as a circle in a Venn diagram, then the intersection of these two would be your inner join. So joins are the commands that you would use to combine the two or more rows, as many rows as you'd like, across different tables. And that's where the power of relational databases come in. Can we go to the next slide, please? Thank you. So there are three types of relationships really in a relational database. Right? So you have a one-to-one, you have a one-to-many, and you have a many-to-many. A one-to-one would be basically every record in one table is related to another record in another table. So we could say every record in donor details table has an equivalent record that is connected to in the credit card details table. So you could, for example, if you have donor X, that donor X has one credit card, that one credit card would appear as a row in credit card details. A one-to-many relationship is generally a record in table A will relate to 0, 1, or many in table B. Right? Now, you could think of as potential donors and donations. A donor might do multiple donations. A donor might do one donation, or potential donor might not do any donations. Then finally, you have many-to-many. Basically, a record in table A can relate to many records in table B and vice versa. Now, these relationships are a bit problematic. And to solve for these, that's what Nick was referring to as you don't have generally something to join on, is what you do is create a bridge table, right? You need something that will allow you to go across different tables. Now, SQL databases are very important integration mechanism in most entities. However, as we were talking about joins, you must have realized that they're pretty poor at representing the relationships themselves. So basically, they do not add semantic value, right? And one of this problem is the fact that you have to create a donor bridge table to go from one table to the other. Can we go to the next slide, please? Another issue with relational databases is something called an impedance mismatch problem. Technically speaking, you can think of it as, say you have a flashlight, right? And the flashlight works off of 2 AAA batteries. But you decide for some reason to link that flashlight to your car battery. Don't try that at home, but the result will probably be you'll burn your flashlight. Similar to an impedance mismatch problem. The impedance mismatch problem appears where your database is a relational database, but your software is something like Python or C or Java, for example, right? Another way to look at the impedance mismatch problem is to the left, you have a receipt, right? Any receipt. It could be a receipt for a donation or any other receipt. Now, that receipt is a whole, but you have to take that whole apart and input the information in different tables, right? And then when you want to then recreate this, you have to join all these different tables back, which is a bit inefficient And if you deal with joins, you come across instances where the join will just simply fail. Can we go to the next slide, please? Another issue with relational databases is basically they're great for a certain amount of data, but with the rise of big data and the rise of traffic created by large websites, you run into a problem, which is a scaling problem, right? So relational databases were created and designed to work off of one specific node. Now, there is limitations to how big that one node can become, right? So another solution would be make it work across multiple nodes. So instead of buying one huge node, you buy different nodes. Now, problem with that is they weren't designed to work off multiple nodes, right? So what is then the solution? If relational databases are great, most of the world runs off of them, but also they present a lot of challenges like impedance mismatch, scaling problems, and semantic value in the relationships. So the solution to that would be, we go to the next slide, please. Object databases, or commonly known as NoSQL databases. No here is a bit of a misnomer because no really means not only SQL, right? It's not that there's no SQL whatsoever. And also the fact that NoSQL itself is a term that was coined off of a Twitter hashtag just to represent the meeting that was happening in one point of time, right? Now, these NoSQL databases or object databases, they solve for the impedance mismatch problem. They're great at handling lots of traffic. They can work off of multi-node system. They're not relationship-based, and they are schemaless, but that doesn't mean you can't have a schema. You can have a schema. So next slide, please. So what are the different types of object databases or NoSQL databases? So from left to right, this is from the least complicated to the most complicated. And your choice should really depend on the kind of data that you are storing. So the key value, basically, it's one of the simplest forms of databases. It's inherently atomic, right? And the best example of that is, say you have a file, right? And that file has a file name. That file name is your key. The link between the key and the value, which is the data within that file, would be the file itself. Now, next comes the white column databases. Now, here, as you'll notice, we're getting a bit more complex. These databases are multidimensional. That's the most important thing. And they are sparse. So what that means is you do not have to have every single cell populated. And what that makes them really good to handle high scale, high volume, real-time data sets. So like if you're capturing information like real-time pricing or some real-time medical information, any such data, you would probably go for white column. Then we go to document databases. Document databases are really good in that they assume the document is the most basic unit. So by that, I mean, if we go back to the receipt example I gave earlier, instead of taking that receipt, splitting it into individual parts and taking each part and setting it in its separate table, what you end up having is all the information relating to that one object resides in one place. And you have a kind of inheritance. So that means there's a hierarchy. So every data point inherits something from the previous data point as you go down. And these are great way if your data is mutually exclusive in that you can create some form of taxonomy around it. Think of it as a JSON file representing the data. And then finally, you get the graph database. These are the most complex forms of databases. They are used when the focus really is the relationship between the entities rather than the entities themselves. A great example of the use of graph databases is back in 2019, a huge Medicare fraud was uncovered in the US. And doctors found out that a lot of, the FBI found out that a lot of doctors were actually charging patients in Florida. But then when they took that data, and that data actually resided in tabular format, and they put it in a graph database, what they were able to identify is the fact that these doctors were duplicating certain charges. So for example, you'd go with one wrist that is broken, you'd end up, the Medicare system would be charged twice for two wrists that are broken. And the reason they were able to visualize that easily is the fact that those graph databases are great at reflecting the strength of the relationships, right? Now, again, this information sat in a table. However, with a table, it's hard to easily visualize. Can we go to the poll number 2, please? So really here, the question is, we know that 70% of you use relational databases, but is it because you use relational databases because that was what is available? Or now that you know that your database should be chosen based on the type of data that you actually capture, what technology would you consider using? Interesting. 25% set graphs. To be honest, I was not expecting that. And 50% relational databases. And that's actually expected because, again, there's nothing easier than to represent most data in rows and columns. We're all familiar with that. And they are less costly than other options out there. Can we go to the next slide, please? Now, let's talk about some other aspects of data storage. Storage is expensive, right? You don't want to be storing data that you generally don't need. So it's important to identify data that is redundant, that is trivial, and that is obsolete. Redundant data would be duplicated data points and records. So for example, the same donor appearing twice in the donor table would be an example of a redundant data point, or certain files saved multiple times where the file could be saved as version 1, version 2, version 3, but there are actually no differences when it comes to the versions themselves. They're simply, you've resaved them a couple of times. Then you have trivial data. So these would be things like your spam email, your session cookies, and any form of data that you are storing that doesn't add any value, doesn't answer any business questions that you might have, and legally you're not obliged to store. And then you have obsolete data. So these are the deactivated phone records, your old email addresses, and any outdated documents. Now, important note here is that before you actually go and clean up your database, it's very important to familiarize yourselves with the rules and regulations about what kind of data you should be storing and for what length of time before you go about deleting the data. Next slide, please. Great. Now, I'm gonna go quickly over some data security when it comes to data storage. Some of it I'm sure you're familiar with, especially like education. For example, never share your passwords. Always be aware of phishing and spam emails. If your data is gonna be compromised, it's most likely gonna be through a phishing email. Always back up your data. Don't leave all your data in one location. Utilize the cloud. Passwords, use password generators to generate lengthy passwords. We all fall into the trick of having, the same password for multiple different accounts where we just, use our birthday and then add a letter or a number at the end. These can be easily cracked. Pseudonymization. So make sure that personal data is pseudonymized. Data should not be attributed to a subject, right? I shouldn't just look at at a table and be able to identify who that individual is, or to what individual this data relates to, right? Not everyone in your company should have access to all the data. Access should be privileged depending on need and business use case. And finally, use encryption, tokens, and hashing. So you've got a lot of off-the-shelf encryption offerings like Microsoft BitLocker, Apple File Vault, and a lot of third-party programs out there. Next slide. I think we're done. Okay, we're done. Well, thank you very much. And we're going to open it now up for questions now.
Great. Thank you both so much. I, for one, learned a lot today, and something that I'm surprised about. So thank you so much. This was a great session. We have quite a few questions, so I'll try and whip through them as quickly as we can. The first question is, Nick, I think you talked about this idea of data domains, and that logically makes sense. But I think it's sort of a mindset in how do you start thinking about data in that way. Do you have any kind of practical tips for how we should start taking our data and think about organizing it around this idea of domains? What are kinds of the key things that you've thought about and used your years of experience to kind of do this successfully?
So I spoke about a conceptual data model, right? And that concept, if you look at that conceptual data model, most of those data concepts are the domains. And typically in those data concepts, I don't mix nouns. They're single nouns: payments, people, accounts, statements. I'm not using two nouns. I'm not saying, payment accounts or payment statements, because that would be joining two domains together. So really use that conceptual model to help you understand the domains that you want to model out. And those tricks of language will help. Try and keep it, if you keep it to single nouns, that will help you to give you a steer towards those domains.
Great, that's really helpful. And then also you can probably use those sort of similar language tricks to think about relationships, has a versus did something to, receive, sends.
Yep.
Sort of more of those verb phrases can start to get us to what the kind of relationship between some of those domains might be.
So the verbs tend to give us the actions. I'm going to do something to it. I'm going to make a payment. I'm going to settle an account. And then the is a, has a kind of statements then give you the relationships. Understand things like, is this really something new, or is it just a specialization of something I've already got? So if you start to use those language tricks, that'll help you a long way on getting those domains sorted out, and in the sort of, you'll organize your data based on that.
That's super helpful. Thank you. I will keep those tricks in mind for myself for sure. A little bit of a question around the kind of technology and the solution that you're using from a perspective. I guess we talked a little bit about, and Salim, I think you mentioned this, which is really around thinking about the kind of data that you want to store. But wondering, and sort of one of the examples that you gave was a little bit more on the usage. How do you separate or think about the kind of data you want to store versus how you might be accessing or interpreting or kind of using at the end state some of that data, and how might that impact the tool that you're using along the way?
Sure, that's a great question. Well, it all starts with really the business questions. What are you trying to solve for? Right. Once you figure out what you're trying to solve for, that's when you start looking at your data and trying to figure out what is important to you. Right. So I think there was a question in the Q&A that actually touched upon that, which was the difference between things like a key value database versus a document database. So really the difference is a document database allows for more complicated key value structures. right? So again, this is about the data. If your data is simply something along the lines of you want to quickly search for certain items using keys, right? Then the key value is great. However, if your data includes certain inheritances and structures, hierarchical structures, then a simple key value wouldn't give you the perfect picture, because you technically would want to search for objects across different, you want to pivot across different points on those objects, right? So going back to the question of the receipts, you have an ID, order item, price, credit card information. You might want to pull that receipt itself using any of those different attributes. And that's where something like a document database comes into play, right? Because it allows you to store all this information in a hierarchical format into one place, as opposed to with a key value, it's just this receipt has that ID. And unless you know that one specific ID, you can't really search for it. So going back to how do you go from what type of data you have to how to actually use it, it really, again, I'm kind of repeating myself, but it's really what are the questions you want to solve for, and it's also a matter of cost, right? At the end of the day, with increased complexity come increased costs. So how much are you willing to pay for that database solution?
Yeah, that's helpful. And I imagine it's also, in addition to the question you're trying to answer, it's also other questions you might have around performance, like how fast do you need data
Yeah,
to
exactly.
be returned to you? How much data are you expecting to get in response? All of those sorts of things probably also feed into kinds of those considerations.
Yes, exactly. So if your data isn't large enough, you could use something like a key value if you also want a quick turnaround when you're searching. If your data is large but is not real time, you could just go to a relational database. However, if you're storing for some reason real time data that's coming in quickly, high volume, high density kind of data, you might end up being better off with something that is multidimensional and sparse.
Yeah, that's really, really helpful. I guess sort of as we're thinking about all these different considerations, one thing that comes to my mind is, how detailed should we be in sort of defining some of the data models that we have and what we expect to see in all of this data? Is it a question that we should spend all that time up front? Is this something of like we see how well it works and then go back to the drawing board? What are sort of your tips or sort of gut feel around those kinds of questions?
As I said, be iterative. Start small. Write down what you know and is fact. Then start to add complexity into it. I would say that if you can be as accurate as you can at the time, use that. As you learn more, modify the models, and then iterate round. Because I think sometimes, to your point, Ashley, I think sometimes you can get into a analysis paralysis kind of thing with a data model, and actually you find yourself caught in a loop, thinking, well, what do I, where do I finish? Where do I start? If you use that premise of modeling what you know, and then expanding it out, and then what the model should really do is answer your questions. And if it answers all of your questions, it's a good enough model. If it doesn't answer your question, then extend it to answer the question and keep going. And that's really what it's all about. And that's how we do it in JP Morgan. If we've got a new question and we can't answer it with what we have today, then we extend the models to answer the question and put the extra data into it.
Yeah, Nick, I love that. I think we not only do we talk about this in our team, but it's something that I've heard over and over again on these sessions, which is really around, starting with something. I think it's about progress and, keeping an eye on what the ultimate goal of that you have, but just getting something down on paper and moving from there. I always say progress, not perfection. That's my my motto. So definitely great to hear that again. One question we had was really around, and I know we talked about a little of this during the session, but what are the best tools that you both use in kind of your uh, daily jobs to do some of what you're talking about? Um, I think people might be surprised on kind of how you're doing some of this complicated modeling work.
So in an enterprise like JP Morgan, I think we almost have every tool available to us in some shape or form. My answer to the question usually is it depends on your technology type. The technologies that Salim went through, that can have an influence of what modeling tools you use. Sometimes the modeling notation itself is quite important. So being able to graphically view models, right? And there's a UML, for example, produced by the OMG, very popular. A lot of people know it. People tend to instinctively know the notation now because it's used so much. And so I think you need to take into those considerations about what your use, who is your customer base, who's going to use it, who's going to view it, what notation do you want, what technologies are you targeting with these models, because you want the most seamless, frictionless development process towards it. And I think if you can answer those questions, then you'll select a set of tooling that will help you. But I would say it's not I couldn't give you, a single answer for every use case because we have so many. So it's just, again, just concentrate on customer base, how they're going to use it, what do they need to know, keep the modeling experience as simple as possible. What technologies are going to use, target tools that are going to give you a frictionless direction towards that, and try and keep the general purpose tools are good for complex situations, but general purpose tools also mean more training, more documentation, more support. So if you have dedicated tools designed for specific purposes, you tend to do better.
Great. Well, I see a bunch of questions around some more detail on some of the specific technologies that were mentioned today. So I think stay tuned for that. We will be in touch with some additional resources, tips, tricks, more details, etc. So I hear that and love the enthusiasm. Before we wrap up, and I think we've heard so many interesting things today, but I just wanted to give both Nick and Salim, one last shot to say, if we were to take away one thing from today's session, what would you like this audience to keep in mind?
I would say there is no one solution to your data storage and organization needs. To re-emphasize something Nick said, depends on the project itself. So don't jump into the more complicated simply because you think it's more complicated. That means it's better. Your data storage might be resolved in a simple relational database and you don't need the others. So it's, there is not one silver bullet, and it all depends on your use cases and needs.
So I would say try and model. Don't worry about the tools. You can write it down in Office documents. You can write it down in Excel spreadsheets, right? It's a process of maturity to get up to that level of sophisticated modeling and fully integrated software development. Just writing stuff down in the first place and knowing this information is a great start, right? That is data modeling. And a lot of people do data modeling without realizing they're doing it. So I'd say start the journey, write it down, and progress.
Fantastic. Thank you both so much for your time today. Thank you to our audience for taking time out of your busy day. I hope that you found this session as valuable as I did. As I mentioned, we'll be in touch with some more details. And with that, I hope you all have a great rest of your day and more on the data journey to come.